Hi, good morning, everyone, and welcome to today's Industry Updates Panel Session 2. My name is Larry Tucker, and I will be your moderator for today's session. Today, we have a number of speakers covering a range of topics from processing to measurement and quality. Starting off, we have Alexander Danelich, who is Global Commercial Director for Crown Iron Works, who will describe innovative approaches for simulation of plant processing operations. Kerri-Ann Blake, Product Manager, Metrohm USA, will highlight approaches for determination and prediction of oxidation stability and rancidity. Ernesto Hernandez, Principal Consultant for Advanced Lipid Consultants, will address challenges associated with processing heat-sensitive oils. We also have yet a couple of more speakers who will talk about measurements of color as well as other measurements of oils for quality. This session will be followed by a panel discussion where you can answer all your questions. At the end of each speaker, there will be about 5 minutes for questions and answers. If we don't get to your questions there, please stay tuned for the panel discussion following at the end, where we'll try to get to most of your questions. Again, welcome everyone, and thank you for attending. Let's move on to our first speaker today. That is Alex Danelich. Let me give a brief introduction to Danelich. He has over 15 years of diversified leadership experience with oilseeds industry, spanning engineering, project management, product line management, and commercial roles in a global setting. He has significant experience in process development and implementation, as well as strategy development to enable growth, working with global teams. Mr. Danelich is currently responsible for Crown's specialty segment globally, and we want to welcome him today as our first speaker. At this point, I'm going to turn it over to Alex.
Hello, everyone. My name is Alex Danelich. Thank you for the introduction, Larry. So I work for Crown Iron Works, and today I'd like to discuss how the pilot plant and specifically our innovation center can enable and help with various new innovation, process development, and optimization projects that you may have. My current function is to lead our specialty group, and being an extraction company, or primarily focused on an extraction company, the specialty group is focused on specialty extraction. In today's talk, I'll chat a little bit about what specialty is, at least the way we see it for us, as well as what capabilities that we could offer or our customers could utilize. And then I'll go through some of the case studies that showcase some of the stories where we worked with customers and how that enabled them to succeed and bring their projects to life. So to begin with, I'd like to talk a little bit about what our specialty is and or what it means, at least for us, and some of the sub-segments there. So for Crown, specialty is, we break it up into, it's really a lot of things, but we'd like to organize it around 3 primary things. In today's environment, I'm sure a lot of you have heard about plant-based proteins, and so Crown plays a big role in the plant-based proteins. We've been a big player for soy protein concentrates, and as well as canola rapeseed protein concentrates, and involved in a number of others. We also develop and provide hemp processing technology, ranging from CBD oil to hemp seeds and to hemp oil. And then we have what we call the specialty other, this is basically all other non-standard specialty extraction technologies. And what we call by other, it's non-standard oil seeds. The standard oil seeds we consider soy, canola, and sunflower, with the traditional process of hexane extraction to make the meal. And in the specialty other, we handle any novel solvent or different process, or a different product. And we subcategorize that into food and beverages, nutraceutical, pharmaceutical, fibers, polymers, waxes, as well as various specialty chemicals. And so over the years, we worked with all kinds of products, a lot of, that we all use every day, like coffees, teas, and orange juices, and as well as in the pharmaceutical and nutraceutical arena, we work with rosemary extraction, marigolds, alfalfa, lupins, etc., and many others. We work with orange pulps, onion pulps, coal waxes, and silica gels, calcium carbonates, and numerous other applications. And so, and that's how we think of specialty in our world, at least in the oilseed world, is anything that doesn't fall under those three traditional seeds we handle in our little division. And being specialty, we are connected at the hip to a pilot plant innovation center, because almost anything that comes to our group, or any customer that we talk with, has something new and different, something that we probably haven't fully investigated, or perhaps have some experience but don't have all the details that the customer may be looking for. And so for that reason, we are connected very closely with our innovation center, a big part of which is a pilot plant. Essentially, everything has to be tested for all the reasons that I've just discussed. And it's both for customer's sake and for Crown's sake, so that we can gain understanding of the process, so we can provide the robust equipment to meet the customer expectation, and for customer to also gain confidence that what they potentially would be buying from us, or building the plant, that it will work and they deliver on the expectations they have. Our facility is located in US, in Minnesota, in our headquarters here. And here we are able to develop, to test, innovate, as well as custom process in a real world environment prior to making full scale investments. So we really have a facility that has ranges from R&D to development area to then a miniature full-scale production that was designed and built to look to mimic as best as we could to what we sell. It's controlled from a PLC system with data historians, and it's a highly instrumented system, so you can collect and gather a lot of data and touch and feel what the plant may look like. Some of our capabilities include also, so we do process development, and we many times start from our raw materials and take it all the way to the final product, whatever that may be. And we subcategorize our customers into three main categories: those that have an idea, perhaps they've done some work on a bench scale and would like to see if that's a viable idea and if it can be commercialized. And that's where really we come in and look at that idea with a commercialization lens in mind, and to see if it's scalable and economical way to make that idea in reality. And so for that, we have our expertise, and we have our pilot plant that's fully equipped with various extractors, both percolation and immersion extractors that I'll talk a little bit about later. We have the capability to also optimize operations and then provide training. And the second category is the customers that we call scale up, that already have operations. They put together the process, that potentially have a product already on the market, but the process might not be continuous, or may not be very efficient, and might not be of the scale that they'd like it to be. And this is where we really bring a lot of value of making a continuous process, scalable continuous process with high efficiency. And the third category of customers that we tailor well to is those that already have good established operations and would like to expand their operations, add facilities, expand or gain efficiencies, test additional innovations they may have in mind, or develop some innovations in collaborations with us. And so all of those features is what the combination of our expertise, experience, and our facility provide to get you to market quicker and successfully. So some of the capabilities we have specifically in a pilot plant, again, we are primarily an extraction company, and so the heart of the process typically involves some kind of extractor. And so we have several extractors in our facility. One of them is what we call an immersion technology, where the product is fully submerged in the liquid. And then we have a percolation extractor, where the product is not submerged, but it's being sprayed by the liquid, and then the liquid percolates through the product and then extracts the extractables depending on what they are and what the solvent is. All of our technology is typically continuous, counter-current, to gain all the efficiencies and minimize energy requirement. A very robust, reliable equipment with a lot of history and experience to go with that. As you know, and so there are many examples where we've utilized our equipment, but it ranges from various oil seeds, like I mentioned previously, to proteins, nutraceuticals, various products of reactions, and washing, waxes, botanicals. I mean, and we don't take, the important thing to point out, we don't take these machines off the shelf or some standards. Really, everything is tailored designed. We optimize the internals, the screens, the way the equipment moves to fit the application specifically. There is nothing that's just generic or standard besides the concepts themselves. In addition, in our facility, one of the big value proposition that we bring is in drying and desolventization. This is where typically our customers work with some solvent that is, costly and could be flammable, toxic, or important in some other ways, that it needs to be fully recovered in the process. And so we have drying and desolventization equipment that we can test and simulate to make sure that it's appropriate, but that it fully recovers, or essentially fully recovers, your solvent in an efficient and an economical way. And now we have a number of different desolventizer dryers. We have like traditional, what we call DT, or desolventizer toaster. We have DC dryer cooler. We have a flash dryer, and several other techniques like DDD, down draft desolventizer, and vacuum desolventization, etc., that we can work with for depending on what the application is. Some of the examples that we worked with in the past with our desolventization drying equipment involve silicas and fillers and pulp, toners, polymers. I mean, you name it, we probably looked at it, or at least have some understanding about it. And then how does it all come together? So we typically, sometimes we get involved in a specific piece of equipment, and then the customer has their proprietary process developed where it plugs in. But many times we get involved where the good portion of the process, or full process, gets developed with the collaboration with us in our facility, our R&D and engineering groups. And that's really where, again, we bring a lot of value, is that end-to-end solution. We also pride ourselves in a life cycle approach, where we start many times with a concept, an idea, or a project that the customer comes to us with. Then we go through all the development stage, feasibility testing, proof of concept, confirmation of concept. But then the equipment gets designed, the facility gets built, it starts operating, and then we're there every step of the way, even after that, where the facility gets expanded, if there are challenges that need to be resolved, innovations that need to be implemented, and then the customer gets ready for the next next installation. And we call that a life cycle approach, where we truly there every step of the way and provide that different type of support depending on the stage of the project. And so the full process solution, end-to-end solution, we've been involved in many different applications between plant protein concentrates and algae and antioxidants, and we have installations for omega-3 and petroleum, even petroleum products, where we extract, for example, asphalt from shingles and things like that in the pigments application, and many others. And all of that, we take that with a sustainability mindset, because we realize that the energy is of utmost importance in order to make, one, the process economical, also to that it's environmentally friendly and safe for the operators, safe for the environments, and for always with health and safety in mind. And that's our key measures when we take on the projects and evaluate its feasibility. Not only is it technically possible, but also is it economically viable, and also is it safe and sustainable for many years to come. And so that's something that just overarching all the activities that we do. And I'd like to talk through several case studies that we've done over the years with this approach, and utilizing our innovation center and our pilot plant in order to enable the success to our customers. And through these case studies, I'll try to showcase several of our capabilities and different capabilities that we bring to the table. For example, the first case study that's up on the screen currently, this is where the customer developed a variety of different soybean products through genetic modifications, and again, in today's environment, many times we get involved to enabling the customers to put the best product on the market from a protein standpoint in a plant-based setting. And so the customer really wanted to evaluate all the different varieties that they came up with, and see which one might be the most successful for the end users. And in order to do that, we needed to provide a substantial quantity of products so that they could do feeding trials, end user testing, if evaluation, is this the right variety and is the right bean. And in this instance, we've offered our custom processing capability, where we needed to fully segregate the various varieties and products, and operate on a continuous scale, in a continuous mode that's representative of the facilities out there, and the product that could be produced by the facilities out there, and provide the fairly significant quantities of each of these varieties, ranging from a ton to multiple tons to greater than a couple, 3 tons of each of the variety. And again, we needed to do it in such a way that it was representative. The products were fully segregated, and provide significant quantities. And so we introduced our custom processing capability, where we were able to run our facility on 24 5 basis type operations. We don't typically run weekends in running our continuous full plant. And so the customer was very happy with the end results and the quality of product that we were able to produce, and again, with the commercialization and lens in mind. Another example was also in plant-based protein, but a completely different project, where the customer was coming to us and wanted to come to develop some new way of making. In this case, it was a soy protein concentrate, for example, a better and more efficient process, and perhaps a better product as well. And they had a number of ideas. It's always all confidential. We always operate under non-disclosure agreements. but the concept was that they wanted to come up with a new process that they were developing that could put them in a better competitive position with some of the other producers and suppliers, both from a process standpoint as well as the product standpoint. And they wanted to develop that process, and they wanted also were looking for a partner that would not only help them to test ideas and help them develop the process, but also then help them commercialize it and then support that process throughout the life cycle of this facility. They were really looking for that true partner and not just a bench top or a few pieces of equipment where they could that could help them develop it. And that's what, again, we were able to offer in that case is a partner, and then also a capability to try to test and explore the feasibility and add, modify, and fine tune the ideas that they had. And so what are the results of that endeavor? We've done significant testing for them. We've done significant modeling. So we've collaborated not with just the pilot plant group, but with our R&D and engineering group to pull all that together and to provide that well-rounded solution that the customer was looking for, so that we could explore, validate concept, again, with a sustainability mindset as well, and economical and commercial mindset when we approached it. And as a result, we've entered in a collaboration type agreement where they have access to our equipment, to our staff, to Crown's expertise to develop, to carry out a lot of this developmental and engineering type work, and then hopefully to build the facility that will provide them with profits for many years to come. Another example where we worked with an algae for another customer for a completely different application and completely different ask in that case. Customer wanted to develop a process of processing algae and extracting oil from algae with ethanol in that particular case to be used as a solvent. Algae by nature is extremely fine powder, and typically neither traditional technologies, extraction technologies would apply here. And those traditional extraction technologies is, like I mentioned, either immersion or percolation type extractors with a number of variations, but at a high level, it's immersion and percolation, and neither one, when you work with really fine powders, is really suitable for that. And so customer came to us and asked us to develop something that would work efficiently, again, in a continuous fashion, and on a significant scale. And they wanted to make sure that in that case that ethanol was used as a solvent. And so we took that project on, and we came up with a way to agglomerate the product first before we could feed. So we found a way to work, for example, make an expander work with this product, and it's an agglomeration technique so that the extraction technology could actually handle it. And then we developed the extractor. We were able to figure out what the optimal extraction time, and how much solvent is needed, and temperatures and ratios and all of that stuff. That's just starting with extraction, and then to tie the entire process together so that the solvent could be recovered, recycled, and reused back in the process, and came up with that whole process. And we were able to test it first to feasibility test and pilot testing, and make ourselves comfortable that it will work, as well as, of course, the customer comfortable. The outcome was that the process was developed. It was it was proven, and then the customer did proceed with the purchase of equipment, and then they've installed the facility, and the plant is currently running quite successfully, and it met their objectives and goals, and it was a really profitable endeavor. And and more importantly, we are continuing to collaborate with the customer, try to engage and help them when some challenges come up or new innovation ideas come up, where they'd like to test new different pieces of equipment, and with our capabilities, before they introduce it on a larger scale, we can model it and then test it, and debottlenecked prior to that introduction. Another case study is a completely different technology. In this case, I spoke a little bit about extraction technology, our developmental capabilities, our custom processing. In this case, it was drying technology is what the customer was looking for. They were looking to develop a process for citrus pulp, in this case, to make a functional food-grade fiber additive. It's typically it's typically a waste fiber in this case, and then they wanted it to be dried and ground, and what was key to them that it wouldn't impact the absorbency of that fiber. And so what we were able to bring to the table is our flash drying technology, and specifically milling flash drying technology, where we could reduce the particle size and dry the product at the same time. And again, before it would be introduced on a large scale, we were able to test the concept, do simulations, make a customer comfortable that it's technologically viable, economically viable, and also can be scaled and continuously operated. And so the testing was complete, the data was collected, and then again, the customer proceeded with purchasing equipment, installed it, and the plant is running successfully, and it really met the objectives that they had. And again, this is one of those where we don't just install and fade away, but we stay in touch and continue collecting data and helping the customer to succeed. So that's on a very high level. Just wanted to introduce how our innovation center, our pilot plant, can enable customers to succeed. And again, we tailor to different clientele, all the way from the initial concept idea, perhaps from benchtop, to those customers who are looking for scale up, and others who are looking to expand and really expand their capabilities that they already have, with an efficient, sustainable, safe lens in mind, and also with by introducing our life cycle approach, where we collaborate with different groups and stay there and provide value every step of the way, from ideation all the way through operation and then expansion and gaining additional capabilities. So thank you so much for your time and for giving me the opportunity to talk today. And I'd like to take a few questions if the audience has any.
Hi, Alex. I just had one question here. It's really a great concept to talk about scale up. And so imagine that I'm a researcher and I have an idea, and I've probably gone to the bench and I've developed a proof of concept. At what point in this whole development process is it best to get Crown involved with that discussion? And about what point in my scale up do I need to start thinking about how much material I might need for trials and testing to make this a profitable venture for an idea that I have? So.
Sure. No, that's a great question. Really, that's probably a good idea to begin those discussions once you feel that your idea that you have on your bench, you feel comfortable enough that it has some potential, and then you're starting to think, well, maybe I need to put together some apparatus, some process to see, is it viable? Sometimes on bench it looks fine, but it may not scale or commercialize economically and effectively. Typically, a good time to start talking with us, at least, is once you've done enough testing to convince yourself that it looks like it's going to go. That you may have spoken to a few customers, and you feel like there is interest in your product, and you really might meet customers' demand. And that's where we start, like you mentioned, that would be a great time to begin the conversation and start talking on how much material would you even need to test. And so then you can evaluate, is this something you can produce on your bench? Do we need to maybe put something together from a raw material standpoint to produce at our facility? We start having those conversations and see what makes sense. But typically a good point to start is once you've done enough testing to get a feeling that this is probably going to be something you'd like to drill more into, and that there is interest in the marketplace for your product.
Thank you. All right, we have another question here. It says, what is the hexane extractor size, tons per hour or day for soybeans?
Wow. Yes, thank you for the question. Like I mentioned, what we do at Crown, we don't have anything off the shelf, and we custom custom developed to what the customers asks for. But when you ask about soybeans and hexane extraction, that's what we call the well-developed traditional process, or one of the traditional processes. And so we've been doing it for a long time, and our extractor range from very small, a few 100, 500 ton a day, which is considered for soybean quite small, to all the way to 8 to 10,000 ton a day type extraction. So,
yeah.
But it's really tailor-made to whatever the customer needs.
Yeah. All right. Thank you. Let me look in here in the question box and see if there are any more questions that I have. I had one more question here, and that is, if you looked at the time frame, kind of to get set an expectation about how long this scale-up process and development might take. If we look back at one of your case studies, could you kind of maybe walk us through a timing, kind of start to finish, so we understand how that process works on a timing scale?
Absolutely. Yeah, no, great question. And so that's and it depends. And I really don't like answering the question like that, but I'll qualify that. It depends on which continuum and which type of customer you're at. If you are a customer that just has an initial idea in mind and needs to go through all the testing from start to finish, it will take quite a bit of time. And so, for example, I'm working on the project currently with the team on that type of idea, and we've been working on that project for not continuously, because we're trying to tailor to a number of customers, but we have slots of time that we work with that for the last 6 months probably, and we are getting to that scale up type thing where we've moved away from bench top, and we are now working on the not the big equipment but large equipment. We are starting to test efficiencies and what the real process may look like, and that took us roughly 6 months to get there, and we expect the next maybe 3 to 6 months where we will get comfortable that the project is viable and commercially scalable, and where we make those few tons of material for the customer to start testing and make sure that the product meets their end customer expectations. So it varies, but I would say it could take us up to a year when we start from the idea standpoint. When the customer already has a process in mind, they put something together maybe in their pilot facility or in their facility. It may not be efficient, may not be continuous, but they have something operating. They already have a lot of understanding about the process of what can and cannot be done. They have real good understanding of the product because they already have it on the marketplace, what the value it commands, etc. Those tend to go faster because we already have a lot of a background and a lot of starting points. Again, it really all depends, but that may be 3 to 6 month type of endeavor, depending on how much testing and everything has to go through. And then the other subcategory, the customer that already have established operation, we're looking to expand, maybe test some new innovative ideas that they have to introduce in new. Those tend to go much faster. Those testings may take a few weeks, maybe a couple of months, and then we evaluate together and decide go, no go, no. So it depends where you are in continuum, but I would say it starts from 6 to a year type endeavor to, and it shrinks down to maybe 3 to 6 months type thing to a few months. I hope that gave you some idea. Larry, I think you're on mute. I'm sorry.
We have one other follow-up question from an attendee about your hexane extractor, the pilot size. We'll get to that in the panel discussion. Sure. We have to move on now to our next speaker. If we look at the schedule here, which is Kerri-Ann Blake. Kerri-Ann will be speaking today about oxidative stability of edible oils, an indicator of quality. Kerri-Ann is the product manager at Metrohm USA in Riverview, Florida. She has her PhD in materials science and engineering from University of Florida. Kerri-Ann has had a number of roles working at Metrohm. She joined as a member of our applications team and is currently a product manager at Metrohm USA. Kerri-Ann plays a key role in product support, product marketing, and also has experience in developing and implementing ASTM methods. Please welcome me in having Kerri-Ann join us and speak on oxidative stability of edible oils, an indicator of quality.
Thank you, Larry, and thank you for the opportunity this morning to discuss the oxidative stability of edible oils and fats and how it can be used as a quality indicator for these types of products. The oxidative stability of an oil indicates how resistant an oil is to oxidation, and this is important because increased oxidation can lead to oxidative rancidity. Rancidification is the process of complete or incomplete oxidation of hydrolysis of fats and oils. This can be caused by several factors, including air or oxygen, light or UV radiation, which along with oxygen promotes oxidation and rancidity. Moisture, as well as bacterial growth, and the presence of moisture can also be a factor in rancidification. All of these result in an unpleasant taste and odor, which is not something that we want in our food products. And this is what we hope to avoid with use by, sell by, or best before dates on food and packaging. So there are three pathways to rancidity, so to speak. Hydrolytic rancidity, also called hydrolysis, occurs in the absence of air, but with moisture present. This type of rancidity refers to the odor that develops when triglycerides are hydrolyzed and free fatty acids are released. Microbial rancidity refers to a water-dependent process in which microorganisms, such as bacteria or mold, use their enzymes to break down fat. Pasteurization or the addition of antioxidant ingredients reduce this process by inhibiting the growth of microorganisms or just destroying them altogether. Oxidative rancidification, also called lipid peroxidation, is caused by the degradation by oxygen in the air. This is the main cause of rancidity of lipids, as oxygen is 8 times more soluble in oil as it is in water. During this process, double bonds of unsaturated fatty acids present in oils are cleaved by free radical reactions involving molecular oxygen. This reaction causes the release of bad smelling and highly volatile aldehydes and ketones. How quickly oils and fats go rancid due to the influence of oxygen is dependent on the sample's oxidative stability. For the rest of our discussion today, I will focus on the on oxidative stability and how it can be monitored using the Ransomat method. So there are 3 stages to oxidative rancidity. It begins with an initiation stage, which is followed by a propagation stage, and then it ends in a termination stage. So let's look a little bit closer at these 3 stages. During the initiation stage, lipids that are present in fats and oils are attacked by hydroxyl radicals in the air. This results in a lipid radical that is highly reactive and very unstable. This is the slowest of the 3 stages, as you'll see in some of the upcoming application slides. During the second stage propagation, these unstable lipid radicals react with oxygen to form lipid peroxide radicals, which react with other lipids to form more lipid peroxides and lipid radicals. So this begins what is called a continuing free radical peroxidation chain reaction, or autooxidation, that just repeats over and over again. So this is a cyclical mechanism that results in oxidative degradation of the lipid. The propagation stage is going to be considerably faster than the initiation stage. The final stage is termination, and this stage involves the slowing or the stopping of reactions. Here we see secondary reaction products from the lipid peroxide starting to break down. And these breakdown products can be aldehydes, ketones, alcohols, and carbonic acids. They tend to have lower molecular weights, are very volatile species, and they cause that bad odor or that rancid odor that we sometimes smell. And these breakdown products are what we detect when we use the rancid method. So I'd like to discuss antioxidants briefly, as they positively impact oxidative stability of fats and oils. They can be natural or they can be added. Antioxidants help to combat rancidity by preventing the degradation of the lipids. So in addition to preventing the degradation of lipids, antioxidants also play a role in the defense mechanism of the body against various diseases. So there are many reasons why antioxidants can be added to products. There are 3 groups of antioxidants that I'd like to cover today. The first are primary antioxidants, or chain breaking substances, also called radical scavengers. These react with free radicals and transform them into more stable compounds. They can be natural compounds such as carotenoids, as well as phenolic compounds and other antioxidant species that are found naturally in herbs and spices. There are synthetic antioxidants such as BHA, BHT, TBHQ, but due to some suspected cancer-promoting properties, there's a growing focus on trying to use more natural antioxidants. Tocopherol, or vitamin E, is another phenolic compound that scavenges free radicals and reacts with singlet oxygens. Secondary or preventative antioxidants work as complexing agents. These agents will chelate transition metals, as well as quench singlet oxygen and work as oxygen scavengers. They can also aid in regenerating primary antioxidants as well. A couple of examples here are citric acid, phosphoric acid, ascorbic acid. EDTA has also been used as a chelating agent in foods to reduce metal-induced lipid oxidation due to the presence of iron. The third class of antioxidants are UV deactivators. These will absorb UV light and slow down the oxidative rancidity process. A couple of examples listed are phenyl salicylate, as well as hydroxybenzophenone. Rancidification is a natural process that we would like to be able to predict in order to determine the viability of products that are sold and stored. Oils that remain stable over longer periods of time command a higher price point, as they lead to a higher quality end product. Also, it's beneficial to be able to determine how antioxidants impact the oxidative stability of oils and food products. However, Natural oxidation in room temperature is a very, very slow process, and even longer with any antioxidants present. So we use the Ransomat technique to accelerate this process. Instead of it taking weeks, months, or even years, it only takes hours. With the Ransomat method, we age the sample at elevated temperatures, purging it constantly with air through the analysis, and we detect reaction products by conductivity. We use the accelerated aging or induction time to help determine how long the oil remains usable. There are 4 major components to the Ransomat. There's airflow or oxygen that is added to the sample by an internal pump throughout the measurement. The sample is weighed into a reaction vessel where it's placed into a heating block. There's a measuring vessel to detect the secondary byproducts, and there's the heating block that heats the sample to help accelerate the aging process. The Ransomat has 2 independent measuring blocks that allows up to 8 samples to be measured simultaneously, and the measurement of each sample can be started individually. So if one sample ends, you can remove it and add another sample and then start that process all over again. The operation of the Ransomat is fairly simple. The sample is weighed into the reaction vessel, and the measuring cell is filled with distilled water. We connect the lids and a couple of tubes, and then the determination can be started. During the analysis, the sample is kept at a constant temperature in a closed reaction vessel, and a continuous flow of air is passed through that sample. Peroxides are formed as primary oxidation products via oxidation of fatty acids in the sample. After some time, the fatty acids are completely destroyed, and low molecular weight organic acids, such as formic or acetic acid, are formed as secondary oxidation products, in addition to other volatile organic species. These secondary oxidation products are conducted by airflow into a measuring vessel that contains distilled water as an absorption solution. The conductivity of the water is continuously being recorded throughout the measurement, and as soon as volatile carboxylic acids are formed in the sample, it causes an increase in conductivity in the measuring vessel. The time until the secondary oxidation products occur is called the induction time, and this is a measure of the oxidative stability of the sample. There are 2 evaluation algorithms that are used by the software. The first is the induction time or induction period that's shown in red. This algorithm is used in food applications. The second is stability time that's shown in black. It is the time until a defined conductivity stage has been achieved. And this is usually used for PVC determinations where they're trying to look at a thermal stability. For this talk, we will focus on induction time. So here we have the output of an oxidative stability measurement performed by the Ransomat. The green curve shows the conductivity change over the time of the analysis. The dark blue curve is the second derivative of the conductivity measurement, so the second derivative of the green curve. The light blue line is the evaluation sensitivity, and the second derivative, or the dark blue curve, has to exceed that blue line in order for the measurement to be considered viable. The default here is 1 for most applications. The red line indicates the maximum of the second derivative curve, and this determines the induction time. So what can influence an oxidative stability measurement? Temperature has the most significant effect on induction time. Typical temperature ranges can be from about 80 degrees to 180 degrees Celsius, but I think about 120 degrees Celsius is the most common temperature that's used. The rule of thumb is that a 10 degrees Celsius increase in temperature can lead to 50% decrease in induction time. So ideally, we want to make sure that we have a maximum deviation of temperature of 0.3 degrees Celsius, and that the stability of the temperature have less than 0.1 degrees Celsius deviation. Therefore, it's very important to carry out a temperature correction with the use of a calibrated temperature sensor in order to correct for any deviations. Gas flow has only a very small influence on results. We weren't able to see any changes within plus or minus 10% of the flow change. Sample weight can have a small influence. There can be a cooling effect depending on the sample weight. So we want to make sure that we keep that as consistent as possible. Oops. Here you can see the influence of temperature on induction time. The induction time decreases from 55 hours to less than 2 hours when temperature is increased from 80 degrees Celsius to 130 degrees Celsius. We use an extrapolation approximation in order to show induction time as a function of temperature. Extrapolation to room temperature can provide a rough estimate of shelf life. There is, however, a high degree of statistical uncertainty involved in the extrapolation technique. So just want you guys to be aware of that. There are two models that are available for extrapolation. First, there's an empirical Q10 approach. This is based on the observation that the induction time approximately doubles with each 10 degrees Celsius reduction in sample temperature. The second model also incorporates reaction kinetics. It is based on the Arrhenius equation and it describes the temperature dependence of the reaction rate constant. The Q10 is probably the most frequently used extrapolation method. So when we talk about oxidative stability, the most frequently asked question is, can oxidation stability predict shelf life? The induction time and extrapolation calculations cannot by themselves determine shelf life, and I have to be clear about that. There are other factors that can impact the shelf life of a product that the ransomat just cannot account for. A couple of examples are enzymes, bacteria, and microorganisms, as well as hydrolytic rancidity. The measurements using the ransomat are generally made at temperatures between 100 degrees Celsius and 130 degrees Celsius. In addition to accelerating the oxidation process, these temperatures can cause side reactions which do not occur when samples are stored under normal conditions. For example, volatile antioxidants may be driven out during this process. Also, in measurements with the ransomat, air is continuously being fed through the sample while a typical product is stored in closed containers to prevent oxidation. So in the end, induction time determined using the ransomat only gives an indication which must be correlated with actual shelf life studies with the use of storage tests. Many different types of samples can be analyzed using the ransomat technique. Vegetable fats and oils such as soybean, sunflower, coconut, peanut oil, palm oil, fat and oil-containing products, instant foods, chocolates, cookies, cereals, meats, and sausages, animal fats, butters, fish oils, lards, etc. Increasingly, we're seeing the ransomat being used in antioxidant research, especially for cosmetic products that contain some of the natural oils that are available. So I'm going to wrap up our talk this morning with a couple of just quick examples of edible fats and oils. So here we see a ransomat result of a sunflower oil product, and you'll see that it has a nice shape with that slow initiation period in approaching the propagation and termination step. And we see that the induction time is clearly noted on the curve. A second example is canola oil or rapeseed oil. As we can see here, that the line is not always a completely flat line at the beginning. However, because we're looking at that second derivative, we're able to determine the induction time just as easily for this curve as we were for the previous curve. Oops. There are several standards that are available for edible fats and oils. I have them listed on the screen here. There's an ISO method, as well as an AOCS method, an AOM method, and an ASTM method that's available as well. So thank you for your attention today. This is what I have for you. If there are any questions available, I'll be more than happy to answer them at this time.
Thanks, Kerri-Ann, for that talk on the ransomware. I just had one quick question before we move on to our next speaker, and that is, since we're measuring conductivity and we're using that, does the conductivity need to be calibrated?
For fats and oils and food products, we don't really need to calibrate the conductivity because we're just looking at a change in conductivity. We're not looking at the absolute value. Where the calibration would have to occur, I mentioned stability time and thermal stability tests. In that instance, where we're looking at a specific conductivity measurement, in that instance, we would want to calibrate that conductivity cell.
Great. Thank you very much. I think that's all the questions we have time for at this point, just looking at our schedule. I think we're going to move on to our next speaker and our next topic for today, and that is Matthew Russell. Matthew is the International Sales Manager for the Tintometer company based out of the United Kingdom. Matt is a color control expert with over 22 years experience in solving customers' problems globally. In recent years, Matt has focused on the edible oil industry and their practices and technologies concerning precise color quality measurement. Today, Matt is going to talk to us about what can go wrong when you measure color. So welcome, Matt, and I look forward to your talk.
Thank you very much, Larry. Good morning, good afternoon, good evening, everybody. It's a pleasure to be here, talking to you from Manchester here in the UK on a sunny day. Yes, I'm the International Sales Manager for Colour for the Tintometer Limited. I'm going to be talking to you about colour. Now, the first question I often face with people is, well, why do I need to measure colour? I've got eyes. I don't need colour measurement equipment. Why do I need to spend money with you? I found a recent quote which I think summarised very nicely the fundamental problem with that statement. One says red, and there are 50 people listening, it can be expected there will be 50 reds in their minds, and one can be sure that all these reds will be very different. This is from a gentleman called Joseph Albers, who was a big deal in the world of graphic design and globally. And I think he summarises the issue very nicely. We can picture a colour, we can look at a colour, whether it's a red or a yellow, whatever, but it's very difficult to communicate that and to control that. And what we want is data and numbers. You know, we've been talking about processes previously. They all require numbers, data. So we're all about data. So, colour of oils. We have a wide variety of oils in use all around the globe, different crops for different purposes, the more common such as soya, palm oil, but then the more exotic oils, and increasingly new oils are coming onto the market, but they all have something in common in that they're often refined and processed, and that process needs to be tracked. You have the deodorization, you have the bleaching of that process, where colour is a useful quality control parameter. Reason being, the appearance, obviously, of the oil itself, but more recently I've had conversations talking about how the darker an oil can affect its flavour and other important, consumer parameters. So colour is a long adopted and well used parameter and recognized for color, for quality. The main focus in the oil industry is on redness and yellowness of the oil, and I'll go into that why in a little bit more detail later on, but I just sort of refer to you a couple of common standards that are used by the AOCS and the industry worldwide. The AOCS Tintometer color parameter, according to well-established AOCS methods, looking at the redness and yellowness, and then the Lovey Bond red, yellow, blue neutral color, again, well recognized and detailed in AOCS and other standards, which looks at the redness, yellowness, blueness, and neutral value of color. As I said, we've been in the world of color for a long time. Without going into too much detail about the history of our company, back in the 1890s, the founder of our company, Joseph Lovibond, built the first tintometer, looking at tint or color. He took red and yellow pieces of glass of a variety of shades and realized that he could put a sample, originally developed for beer, put a sample in there, put the different red, yellow and red glass slides in of different, different lightness and darkness, and match his color and get a number. And over the years, this visual method where a human operator would visually adjust redness and yellowness to match a color. It's been through various different reiterations in the 30s, in the sort of 50s and 60s, in the Model D, the Model E. There's still a few of these out there in the market. I believe people are still using them. The AF710, which is used in the United States, specifically for the AOCS tintometer scale. And then the Lovibond Model F, which is still commonly used in the edible oil industry all over the world. Basic operation of the unit is you open that grey lid at the back, you pop the cell in with your oil in it, and you have a series of racks which you can bring into position by adjusting dials, and then you can look down the viewing tube and match the colour. These are the actual racks. If I can bring up a pointer here, I can just indicate to you, for example, what these racks are showing. So on the yellow racks here, we have steps of 0.1 of colour. So from 0.1 to 0.9, and then steps of 10, 20, 30, 40, 50, 60, steps of 1, 2, 3, 4, 5, 6, 7, 8, 9, and then steps of 10, 20, 30, 40, 50, 60, 70. So you can see that by positioning those racks in different combinations, we can go from 0 to 79.9. Same cases with the red, same as with the blue. So this, once you combine the red and the yellow and the blue together, you're getting a very wide gamut or range of possible colors that this visual instrument can factor in. The neutral there is to compensate for brightness of some oils. That's a different topic on another day. So basic principle, you have a human being, a light source, and a glass cell. The cell has your oil in it. You're looking through the cell, through to the lamp, and then you're introducing a series of different glass filters between the sample and you, matching the color. And the operator, once they're happy that there's a visual match, will come up with a red and yellow value, and possibly a blue if you're using the Lovibond scale, and possibly a neutral, defining the oil. So you've gone from it's a yellowy browny oil to I have a precise, or have a number I can associate with my sample. And exactly, this is what you see through the Model F sample viewer. So this is important for our company, so much so that our logo actually represents the Lovibond red, yellow, blue color scale there, with the yellow, red, and the blue. So I talked about why this redness and yellowness, why is that being used, combination of that. What I have here is a CIE 1931 chromaticity diagram, which in simple terms is a map of human color vision, what we can perceive in terms of the visible spectrum. The black triangle is effectively what you're all looking at, which is your monitors. Your monitors have red, green, blue guns or LEDs in them that combine together to give you all the colors you see on your screen. That's the map. It's a color gamut. It's the possible max green, red, blue of your monitor. Now below that, in the slightly fainter line is the Lovibond scale. If I can, oh, let me just get rid of my pointer. Yeah, it's gone. Oh, sorry, one moment. What I've got there mapped is the red shade from the red of the Lovibond scale, the yellow from the yellow of the Lovibond scale, and the blue. And within that circle is pretty much where most people are worried about in the edible oil world. The combinations of reds and yellows, the browns and oranges and yellows of edible oils. You know, a little bit of the green sometimes, but you know, broadly that's where everybody tends to live. So you can see from this scale, it's very useful because we can gather a lot of information, precise information about colour in that part of the spectrum we're interested in. Now, those of you more familiar with the Lovibond scale may have come across this common misunderstanding. We're used to linear scales. I've got a centimetre ruler here, 0 to 30 centimetres. That's a linear scale. The difference between 0 and 1 centimetre is the same as the difference between 29 and 30 centimetres. Because of the visual nature and the nature of the glass used in the original scale, the Lovibond scale is not a linear scale, it's a logarithmic scale, which means you have more precision in the lower values of the scale. And this has practical applications when you're measuring colour with regards to path length. If you're taking an edible oil, you put it into a cell. Depending on the path length of the cell, it will affect the appearance of the colour. Remember, we're talking about the visual appearance of the oil. If I take a range of glass cells, I put the same liquid reference in them, and then I look at them lengthways, you can see straight away, it's very obvious that a 6-inch cell appears a lot darker than a 1 millimetre cell. And this has a practical application. And this is why we recommend that when you combine the red, yellow, blue or neutral values, you always try to have a number below 20 because you can reduce the path length. So for example, if I have a 5¼ inch cell with an edible oil in it, I'm measuring it in a colour measurement device. I'm getting a value around 50 Lovibond yellow. That's actually, you're getting into the realm where you know, as a human observer, you would struggle to spot the difference between 45 and 55. So a way to improve your resolution on the reading is to drop the sample into a shorter path length cell where you will get a lower Lovibond value, but a more precise Lovibond value because of the nature of the logarithmic scale. And this is, again, often spoken about in the standards, but poorly understood. So I always, whenever I have opportunities like this, I like to raise this and to my audience just to say, you don't have to be locked into a particular path length. You can vary the path length, particularly with the Lovibond scale and the AOCS Tintometer scale, to improve the precision of your reading. And if you do have a Model E or a Model F and you're using it, always read the manual because it stipulates this and makes this point I've just made to you about this 20 Lovibond units. Sometimes it's not practical. You know, 20 is, you know, difficult to achieve, but it should always be your goal. Now, we're talking about colour measurement. If we're measuring the oil needs to be transparent. We want to get our light through the sample to the eye in the case of a visual Model F. We don't want light scattering because we're looking at turbidity then as another factor. So it's very important when measuring oils to get the samples transparent, either by filtering or heat. Now, with some oils like soya, oilseed rape, sunflower oil, they're nice, clear, bright oils, often at room temperature, 20, 25 degrees. But when you get into palm oils and some other oils, that can be a real issue. and that needs to be factored into any colour measurement to stop variations in readings, not because of an actual colour difference in the sample, but because of turbidity. Now, we talked about visual equipment, which is still commonly used in the market. But the key thing is that you have variation between observers. So two people may, in a laboratory, may view an oil using a Model F, a visual equipment, or an AF710, and disagree with each other. And the standards, the AOCS standards, wisely refer to use of a third arbiter to check and concur which of the readings is correct, whether it's a pass or a fail. So it's a consensus. Unfortunately, many people are using visual instruments with perhaps one operator who has never been colour vision checked, is perhaps unaware of the possible variation between them and another person. So the standards, the AOCS standards, recommend the use of at least two operators and a third operator when visually checking a system, an oil. In the AOCS standard 13E92, there's actually a table within that standard that stipulate the values that you can be measuring and the expected tolerance of those values. So if you're measuring an oil that's giving you a red value of 5, you can expect on the same equipment in the same lab between different operators to have a repeatability of plus or minus 0.7. In a different lab with the same oil, with another Model F, different operators, because of various factors, there might even be wider variation. And this is because you have a human being making a visual colour decision. So the fundamental issue is the human being making a visual colour assessment. As I said, the methods have taken steps to reduce that, but you need to be careful. So let's summarise. Time and compliance. Compliance with a standard and time are the two key parameters in a lab or in a production monitoring process. In the past, to a certain degree, I would argue people had more time, therefore they could achieve high compliance, particularly with a manual instrument where they're having to take care in making adjustments, fine adjustments to get a colour value. However, in the real world today, we have low compliance and quick measurement. So people need to make fast colour measurements, but you know, because they're making sometimes having to make visual assessments and rush it, they have low compliance. This could be an issue. So this is why we've adopted automatic colour measurement, automatic spectrophotometry, where if you have an automatic system that doesn't rely on an operator making a visual assessment, you can have a fast measurement and a high reading, giving you high speed measurement and high compliance. So this is why, particularly in North America and South America, people have adopted automatic spectrophotometers like the PFXI, and increasingly a new product, the Model FX. These operate as follows. You have a lamp, some optics, a glass cell, a detector. You shine your light through the liquid, your oil, onto the detector, and we convert that into spectral data, which we then can convert into a Lovie-Bond value. If you take the Model FX, it's a benchtop unit, robust, tough for the environments that it's in. It's slightly more compact than a Model F, AF710 or a PFXI. But the key thing here is its accuracy and repeatability. And this can be any spectrophotometer, where if here in this, I have a spectral graph here showing transmission versus wavelength, visible spectrum, give or take about 380 up to about 780, where I've taken amber glass, which is a very stable medium, I've measured it in a PFXI, and for 30 readings, they're identical. If you were to take human beings with their variation and visual assessment, you would not achieve that. We can take a real world sample at a liquid reference in a glass cell and get the similar results. So it's not just a perfect sample. Now, in terms of temperature, as I've spoke about, the transparency of a sample can impact colour readings. Palm oils are particularly problematic, where we know, depending on the temperature, because of the multi-fractional nature of the material, depending on the different fractions, different melting points, it'll have different characteristics. That's why it's so useful. But we know with a palm oil, if you heat it, free samples there, room temperature, slightly heated, nice and warm, nice and clear and transparent. But the temperature of the oil directly affects potentially the readings you're getting. And this is why, particularly with our Model FXs, you have a thermometer in the device as well as a heater. And I'll show you some data proving why that is so critical. A series of palm oils here measured in a PFX, a Model FX. What I'm tracking there is a Lovibond blue value versus temperature. Blue is often an indicator of turbidity. If a sample is showing a lot of blue and it's not green, it's appearing dark to the instrument because the light is getting scattered. Therefore, if we take a series of palm oil samples at 50 degrees, you can see that blues drop right down, which to all appearances, the sample is transparent. However, further analysis, by that, I mean, as you say, I want that. I want the green tick. I want, if I put a piece of paper with some text on it behind my sample, I can see the sample. If we take redness of the oil, again, a critical quality parameter for some, you can see at 50 degrees, you know, we're getting a series of numbers for these different palms, a series of values. If we look at palm number 2, this orange one, my pointer up here, we're getting 3.5, that's dropping probably down to about 3.3. Oh, sorry. And then depending, as we warm the temperature, the sample temperature, the redness value is actually changing. And it fluctuates with some of the other oils as well. And we've had some external customers of ours who've done similar tests and had similar results with their palm oils. If we look at the yellowness here, again, we've seen around 70. We're still getting changes, particularly with that palm oil 2 and that palm oil 7. So you can see that initial appearance of no blue at 50 is not showing the true picture. We need to warm the samples more in order to get a good stable color reading. Now, neutral is an indicator, it compensates for brightness. This is actually interesting what I'm showing you here. In that at 60 degrees, you can see we're getting this increase in the neutral reading of this palm oil 2, which indicates the oil is becoming brighter, more transparent. So taking that all together, for multi-fraction oils such as palm oils, you've got to use the criteria for the longest fraction chain present, as the sample may appear melted, but may not be fully melted, and there may be colour variation because of the temperature. So when we've spoken with some of the biggest edible oil refiners in the world, and they're recognising that temperature variation from site to site of sample for critical colour measurement, if you want to have a tight tolerance on an automatic instrument, you need to control temperature to get good, consistent colour readings. So temperature variation can result in colour variation. So to summarise, correct cell path length is critical. It should always be reported. And if the numbers are too high, you need to consider shortening the path length. Oil samples have got to be transparent, particularly with automatic instrumentation. If you're talking about standards, you talk about red and yellow, you need to be talking, check that you're using the same standard as the person you're talking about red and yellow to. Is somebody using AOCS Tintometer? Is somebody else using the Lovibond red, yellow, blue, neutral. If you're using a Model F or an AS17, you will have to have wider tolerances simply because of variation between human beings. It's written in the standards. If you've got an automatic instrument, because of the inherent stability of the instrument, there's no human being involved in terms of the direct assessment, you can have tighter tolerances because you've got high repeatability and high inter-instrument agreement. Automatic instruments are fast and compliant. You're not cutting corners. And temperature variation will impact colour. Just to say, we appreciate we've got a wide variety of instruments in the market, and our Model FX is designed to have high agreement with both our visual and legacy benchtop instruments like the PFX and PFXi. So if you're in the world of colour, we can talk to you about this. I'm on LinkedIn. It's a bit of self-promotion there. Please feel free to connect to me. I'd be delighted. Loveybond.com, a lot of information on there. We have a new edible oils handbook, which includes a lot of the information and much more than what I've discussed today. Thank you very much.
Hey, Matt, thanks for that presentation. We just had one quick question before we move on to our next speaker, and that is the AOCS tintometer scale also logarithmic?
Yes, exactly the same principle as it's not the same as the Loveybond red, yellow, blue, neutral scale. So both, which is a common cause of confusion sometimes. There's a complicated long story involving the Second World War and U-boats and all sorts of things, which I won't bore you with. But yes, it's a logarithmic scale and it's not transferable. So you can't take a red from an AOCS tintometer and map it directly onto the Loveybond red. You just need to be careful. We can measure both, no problem.
Yep. Okay. Thank you very much. That's all the questions that we have time for at this moment. We need to move on to our next speaker. Just a reminder to our audience, if we don't get to your questions right during this part, we have a question and answer panel following our last speaker, starting at about 9:15 a.m. this morning, Central Time. So I'm going to move on to our next speaker. Our next speaker is Ernesto Hernandez, and he's going to be speaking with us about applications of new short path stripping technology and edible oil processing. Ernesto has quite the bios. He is currently the principal consultant with Advanced Lipid Consultants in Tomball, Texas. He is served on the faculty at Texas A&M as the former head of the Fats and Oils program. He's worked in the graduate food science as a member of the graduate food science faculty at Texas A&M. He has co-authored 2 books, holds 2 patents on specialty lipids and process design, and he has published over 100 articles in several areas of lipid and food product development. Obviously, Ernesto has quite a bit of experience in the area of processing and development of fats, lipids into food products. Please welcome Ernesto Hernandez, our next speaker.
Hello, everyone. Welcome to the presentation, Applications of New Short Path Stripping Technology in Edible Oil Processing, by myself, Ernesto Hernandez, from Advanced Lipid Consultants, and Perry Alasti from Artisan Industries. This presentation will include a quick introduction on the general aspects of edible oil processing. Then we will talk into more detail on Artisan's multi-stage short path stripping technology compared to the single-stage short path distillation processing. Then we're going to applications of this new artisan technology in edible oil physical refining, removal of contaminants, and also on the concentration of omega-3 fatty acids. Edible oils are generally processed to remove impurities and contaminants to meet regulatory and quality control standards. Components and impurities normally removed include free fatty acids, phospholipids, color components, peroxides, carboxylic compounds, and other environmental contaminants. Most edible oils undergo 4 basic processing steps: refining or neutralization, bleaching, winterization, and deodorization or physical refining. The last step is usually used to remove odors or flavors, and in the case of physical refining, to remove free fatty acids and other environmental contaminants. And it is in this last step where short path distillation has a great deal of potential. This slide shows the difference of processing of the 2 major edible oils globally, which is soybean oil and palm oil. Soybean oil is normally refined using caustic or sodium hydroxide solutions to neutralize the free fatty acids, and palm oil uses physical refining to remove free fatty acids by distillation. Oils like palm oil, palm kernel, and coconut are usually refined by physical refining, which basically means removing the free fatty acids in the deodorizer. This is due to the fact that the free fatty acid content of these oils is relatively high, and it's more economical to remove the free fatty acids by distillation. Oils like soybean, canola, sunflower, corn, on the other hand, have a lower content of free fatty acids, and they can be more economically refined using caustic refining. The difference between these 2, chemical and physical refining, is that chemical refining is carried out, the deodorizing part, at lower temperatures and also lower residence time. In physical refining, the deodorization takes place at higher temperature and higher residence time. As a result, there is the disadvantage of generating some process-derived contaminants such as GEs and MCPDs, and also the cost can be higher. Later on, we will see how the new artisan evaporation technology will be able to mitigate these contaminants and also to use this technology as a physical refining method. Another issue with edible oils, especially oils like fish oils, is the presence of persistent organic pollutants, such as dioxins, furans, PCBs, pesticides, and brominated flame retardants. And in many cases, these oils have to be processed by molecular distillation in order to meet regulatory standards. Besides environmental pollutants, we also have process-derived contaminants in edible oils, such as trans fatty acids, polymer, cyclic compounds, MCPDs, and GEs. More recently, process-generated contaminants such as MCPDs and GEs in some refined oils have become a concern. For example, in palm oil, which has some of the highest content of diacylglycerides, and the use of high temperatures and long residence times tend to generate these contaminants, MCPDs and GEs. MCPDs and GEs can be genotoxic and or carcinogenic, and as a result, regulatory agencies in North America, Europe, and Asia have set up strict limits for the presence of these contaminants in edible oils and many foods. As a result, the industry has started to implement several methods to remove or mitigate the presence of MCPDs and GEs. Some measures include bleaching or post-bleaching, and also post-deodorization. And more recently, some processes have been successfully introduced that use short-path distillation. An area where short-path distillation is commonly used is in the production of omega-3 ethyl ester concentrates for pharmaceutical and supplement applications. Basically, fish oil or other omega-3 oils like microalgae oils are transesterified with ethanol using a catalyst to produce these ethyl esters of the fatty acids of the fish oil or other marine oils. Once the ethyl esters are produced, then they are subjected to short-path distillation, where the shorter chain ethyl esters are distilled off and the EPA and DHA ethyl esters are concentrated. However, there is a limitation. In general, the short-path distillation will be able to concentrate only up to 50% EPA and DHA. As a result, other technologies have to be used to further concentrate these omega-3s to achieve the supplement and pharmaceutical requirements. For example, the use of urea crystallization that can concentrate further EPA and DHA up to 84%. Later on, we will see that the new artisan multi-stage evaporation technology is able to replace the conventional short-path distillation and be able to achieve much higher concentration of EPA and DHA. This slide shows the difference between thin film evaporation and short-path distillation. In thin film evaporation, the vapor generated from the falling film travels into the vacuum system, whereas in short-path distillation, the vapor generated from the film travels a short distance into a condenser. Molecular distillation normally refers to the use of an apparatus where the gap between the evaporating surface and the condenser is equal or less to one mean free path of the molecules evaporated, thus facilitating collision-free transport, as illustrated in the equation below, where the free path is generally estimated from the vapor pressure, the molar mass, the gas constant, and the temperature. Short-path distillation generally operates at very short residence times, high vacuums, and the distance between the evaporation and the condenser is very short. As a result, we have very efficient mass and heat transfer, and the condensation of the vapor generated into the internal condenser is very quick. Common configuration includes thin film generated using devices such as rollers and wipers, fixed clearance blades or pitch blades rotated inside the column to spread out the film. Artisan Industries offers a new thin film, falling film evaporator equipped to overcome the problems associated with film distribution in falling film evaporators. In the standard design, the feed introduced at the top of the unit cascades down as a thin film through a series of tube and disc trays, where the volatile components are stripped into the vacuum system or condensed in an internal condenser for more efficient recovery of the condensate assay product. Evaporation takes place through several stages, where each tube and disc tray creates a fresh liquid film at each stage, providing a new surface for evaporation and condensing. The basic design has semi-cone solid distribution discs for moderate vacuum applications. The system is also designed to operate at high vacuums. This diagram shows two options of the new artisan multi-stage thin film evaporation technology. In the first option, we have a system where the vapors generated travel out of the evaporator into the vacuum system through the size or the chimney in the evaporator. In the second option, we are introducing an internal condenser. So in this case, the vapors generated do not travel into the vacuum system, but instead they are condensed on the internal condenser and fall out of the evaporator as a product, as a true short path distillation technology. The first application to be reported is the use of artisan multi-stage short path distillation technology to physically refine palm oil. And we successfully removed the free fatty acids and refined the palm oil to meet commercial standards with, for example, reducing the free fatty acids from almost 4% to less than 0.1%, also reducing the peroxide value. And as we can see, the triglycerides also increase because the short path distillation multi-stage evaporator also removes monoglycerides and diglycerides. And as a beside point, we also notice that the removal of tocotrienols is minimal, and this would involve some optimization trials according to the customer's needs. The artisan multi-stage short path evaporator was also tested to mitigate the content of MCPDs and GEs in palm oil. And as is shown in the slide, the artisan's short path evaporator was capable of reducing glycidyl esters and CPDs to within regulatory standards. The artisan multi-stage evaporation technology was successfully used in the concentration of omega-3s, specifically omega-3 ethyl esters of EPA and DHA. Normally, systems of molecular distillation can concentrate only up to 50% EPA and DHA. As a result, other technologies such as urea crystallization have to be used. The artisan multi-stage evaporation system is capable of concentrating above 50% EPA and DHA for supplements and pharmaceutical applications. This system also is successfully applied in other oils such as flaxseed and microalgae oils without destroying the nutrients such as EPA and DHA. 100% of the omega-3 fatty acids are preserved, and as an added advantage, as mentioned before, the multi-stage artisan evaporation system is used to remove glycidyl esters and MCPDs that are also found in some marine oils. The new artisan multi-stage thin film evaporation technology has been successfully applied in several other applications. So far, we have covered the use of this technology in the physical refining of edible oils, also in the removal of environmental and process-generated contaminants such as PCBs, dioxins, GEs, and MCPDs, and more recently on the concentration of omega-3 fatty acid ethyl esters that are now widely consumed in some supplement and pharmaceutical applications. Other applications of this multi-stage thin film technology is in the concentration of mono and diglycerides that are widely used as emulsifiers, the removal of other contaminants from oils like citrus oils, also in the recovery or removal of cholesterol from animal fats, the purification of essential oils, and also the recovery, which is not listed here, of antioxidants. And more recently, the recovery of squalene from shark liver oil, olive oil, and amaranth oils. The Artisan multi-stage thin evaporation technology offers several important advantages over commercial deodorizers and molecular distillation systems. The Artisan evaporator operates at lower temperatures and lower residence times. Therefore, there is no generation of process-generated contaminants, and also no deterioration of the nutrients of the edible oils, such as omega-3 fatty acids. Compared with molecular distillation systems, the Artisan multi-stage evaporator has the added advantage that it has no internal moving parts, and also it is a true multi-stage evaporation system. And the Artisan evaporator has the added advantage of having an internal condenser that allows us to recover the condensate as a product through the internal condensation system. This allows for a more efficient heat and mass transfer and avoids having to use multiple units, as is the case of conventional molecular distillation, where multiple systems have to be used in order to achieve the required concentration levels or required purity of the product to meet regulatory standards. We are estimating that this innovative design by Artisan for a short path system allows for more than 50% savings in capital expense, operation and maintenance costs in most deodorizing and distillation operations.
Hi, Ernesto. Thank you for that presentation. We have a quick time for a quick question, I hope. We had one question here. It said, would this technology be able to achieve GE less than 0.05 parts per million?
Yes. Just think of this technology as, in fact, we believe we can replace many of the processing capabilities of normal molecular distillation. So we have been able to process palm oil, for example, which lately has been found to have higher amounts of these processing contaminants to within regulatory limits. It's just a matter of the starting content of these contaminants in the starting material. You can adjust residence times, you can adjust temperatures, you can adjust feeding rates and that sort of thing. So that's the advantage of this system. It's very versatile. You can modify, for example, the number of theoretical plates inside the system. So it's very versatile, very innovative.
Yep, that's very good. We have time for one more question here, and I'm going to try to pick one that's going to be a quick one. It says, what would be a typical pressure drop through the stripping column?
That is a great question. And that is the advantage. And again, having such a versatile system, you can choose between having an internal condenser, which means the vapors produced or generated are almost immediately condensed. So your pressure drop is minimal. Now, if you choose not to have an internal condenser and instead have the vapors being exhausted into the vacuum system, then of course your pressure drop will increase, because of the vapors having to travel such a distance and the vacuum system having to work to evacuate this vapor. So the pressure drop will increase there. But you have the choice of having an internal condenser where you minimize the pressure drop, and it actually allows you to have very high vacuums, just like in conventional molecular distillation.
I think that might be all the time we have for questions at this point. We have some more questions, and I would remind the audience that we will be having a Q&A session after our next speaker, Christopher Clark. So please stay tuned. We want to get to your questions and make sure that they get answered. And Ernesto, thank you very much for sharing this information and talking about this new technology. Our next speaker is Christopher Clark. Christopher is going to be talking with us about process automation using Fourier transform near-infrared spectroscopy with a focus on applications in the oils and oilseed industry. Christopher is an application scientist specializing in FTNIR process analytics for Bruker Scientific. He has over 15 years of industry experience in the field of process analytics, including the last 4 years with Bruker. Welcome, Christopher, and I'm going to turn it over to you.
All right, thank you, everybody. So my name is Chris Clark, and I'm an application scientist with Bruker Applied Spectroscopy, focusing in process automation using near-infrared technology. And I'm going to talk a little bit about its application in the oils and oilseeds industry. So I'm going to start with an intro into the technology itself, and then talk a little bit about its current uses in the industry, and then how to apply it online, or where it can be applied online. So near-infrared spectroscopy is a type of light absorbance spectroscopy that is, or a type of absorbance spectroscopy that uses an incident light to irradiate a sample, depending on the type of sample you're using, or the opacity of the sample. That some of the light is going to be absorbed by the sample. And that light that is not absorbed is either going to be transmitted or reflected to a detector. And then we use the ratio of the light that reaches the detector to the incident light. And through a mathematical transformation, we arrive at something called Beer's law, which is just a mathematical formula that allows us to use that ratio of absorbed light to quantify the constituents of a sample, or constituents within a sample, using the absorbance, setting it equal to the path length, which is just the distance the light will travel through a sample, the molecular extinction coefficient, which is just a unique characteristic that a sample has to absorb light at specific frequencies, and then to arrive at the analyte concentration, which is, of course, the thing we care about. It's a type of vibrational spectroscopy, which means that it is using the frequencies of light to activate specific intermolecular energies in a bond. So there are different vibrational motions that occur, and they're the result of changes in dipole moment in covalent bonds between certain atoms. Bruker uses a type of spectroscopy called Fourier transform spectroscopy, which uses an interferometer, which just consists of a beam splitter and a mirror, and a series of 2 mirrors that will take an incoming light source, split up the frequencies of light into 2 equal intensities, and across a moving mirror, a motion of the mirror will create interference patterns with the light that will allow us to get at information of the sample when the light actually hits the sample. So there are different configurations of interferometers. There's flat plane interferometers. Bruker uses a type of interferometer called a cube corner, whose purpose is really to provide stability over the use of a spectrometer, to allow it to maintain precision over increased use over a long period of time. The technology, or the light that actually crosses an interferometer, contains multiple frequencies, so it's not a monochromatic source. So what happens is as the mirror moves, the motion will start to create this sum of signals. So you'll get, as the frequencies go across at different frequencies or different mirror positions, you get this sum of signals that will eventually result in this interferogram. And interferogram is going to contain the information of the sample. So through a Fourier transformation, that takes us from the measurement in the time domain, which is where we obtain the interferogram, to a spectrum in the frequency domain. We can arrive at a single channel spectrum for a sample. And we then take the ratio of that single channel spectrum over the ratio of a single channel background to arrive at an absorbance spectrum. And it's this absorbance spectrum that contains the information from our sample. And from there, we're able to build a calibration. So NIR spectroscopy is a type of secondary method of analysis. So it requires a calibration to a primary method where you'll take a sample and you'll measure it both with the NIR and using the primary method that is currently being used to obtain spectral data and a range of reference values for any of the constituents that are of interest in the sample. And then you will build a calibration model that will allow you to then take unknown samples, run them using the spectrometer, and arrive at the quantitative information for all of the constituents that you are interested in measuring in a sample. So it's a way to consolidate a variety of different, more time-consuming wet chemistry techniques and arrive at a single concise answer for all constituents of interest. And here is just an example of the result of a calibration. This would be one for iodine value in edible oils. What you're seeing here is the predicted value versus the true value, the predicted value on the y-axis, the true value on the x-axis. So this is an example of what a calibration might look like that you would then employ to predict true unknowns in a QA/QC environment. One of the advantages to the principle of Fourier transform technology in near infrared is the ability to transfer methods between spectrometers. This is due to the precision in calibrating the x-axis for the spectra that are obtained. And what this allows you to do is once a calibration has been developed, you can employ that calibration to any identical process anywhere in the world on any instrument without having to recalibrate or redevelop a calibration from site to site. So it provides kind of a long-term stability and an ease of transfer between FT instruments. Now, NIR is not a new technology in the oil industry. It is a well-developed, well-proven technology that is used for a variety of oil seed and oil types to quantify a variety of different constituents, IB, free fatty acids, trans fatty acids, fatty acid profiles, different in oil seeds, different values, moisture, protein, fiber, ash, fat. And Bruker actually has a fairly extensive catalog of a lot of these calibrations that are already developed. In addition, the AOCS recognizes NIR as a standard procedure for reflectance measurements for oil, moisture, and volatile matter and protein. And they have analytical guidelines for the management and development of models. What tends to be less well known or is not as well appreciated is that almost any application that can be successfully performed on a benchtop can also be transferred to be used in line. So Bruker has a variety of options of probe types and designs available to allow you to go from benchtop analysis to inline process automation to get at the same results and the same quantification of your constituents for different products. And this is just there are many different types of inline setups that you could envision in a variety of different applications. The example I'm going to use here is for a soybean installation, just a typical soybean installation where you have a centralized spectrometer. You can see on the right side of your screen, and you have it in a control room leading out into the process area. In this example, we have it set up to 6 different sample locations, all in process. And you could envision in a soybean installation from the incoming beans through their process, the processing of the beans themselves, and then even potentially an extraction for crude oil, putting a measurement that would allow you to automate the results you obtain as the beans are going through the various processing stages in production. The results can be sent out to a DCS or a control room, so the entire process, the entire production can be automated. And so that, and again, with, in many cases, the level of reliability and precision that can be achieved, or a similar precision that can be achieved in a benchtop application. This is just an example of a potential installation for soybean analysis. So this is a meal line where you have a reflectance measurement, a reflectance probe that is installed, in this case, just above an open conveyor. In many cases, you'd see it attached to the side of a conveyor or a chute or a hopper. But you can see the light being shown onto the sample itself, so it's reflecting, and the information that is contained in the return light will provide us information about the constituents of the sample. In this case, lowering it into the sample to achieve a desired path length distance between the source and the sample itself. And this allows us to get at sort of a real-time trending to be able to quantify the constituents in production without the need for the time delays or the costs or the infrequency that would otherwise be seen if you were doing everything manually. And you can see this is just an example of fat trending over time. The orange line represents the results from the spectrometer, and the red X's represent grab samples that were pulled and run to test against the results of the spectrometer. And you can see a pretty tight correlation with how the analyzer is actually reading versus what the lab results are showing. So this is conceptual proof that you can use this technology to accurately monitor your process in more real-time fashion. And so we're going to make it fairly short and sweet today, but that's my intro to near-infrared as a process tool for automation in the oilseeds and oils industries, and stay happy to take any questions. Thank you.
Yeah, Christopher, thanks a lot for that presentation. Just had one question. Since we're looking at comparing a primary method, I mean, could you maybe comment a little bit on the how closely we might check compared to a primary method?
Sure. So it's going to be a little bit dependent, of course, on the precision of your primary method. So there's always the need to kind of understand what the error of your method is. But we've seen in practice, especially in a lot of the oil applications themselves, where in many cases the results of the NIR analysis or the NIR calibration can be as accurate. You can't get more accurate than the primary method, of course, but in some instances you can improve on the precision of the primary method. So there is the ability to achieve the accuracy of the primary method, and in some cases to even improve on the precision of the primary.
Thanks. And just one other quick question. Is there a maximum length where we can run the fiber from the instrument when we're trying to automate a process?
Sure. It depends a little bit on the probe type. Generally speaking, for a reflectance measurement, you are going to want to stay within 100 to 120 meters. And then for certain types of transmission measurements, you can go longer than that. 150 meters or even a little above that is possible.
Well, listen, thank you very much for this presentation. At this point, I think I don't have any more questions, and I'm looking in the questions box. We have a number of questions for all the panelists. Since we finished up a little bit early at this point, Amy, I'm going to try to open it up for our Q&A session. If we can move into that, we may finish up a little bit early today, but I know there are a number of questions that have come in for all the panelists. So if we can move into our general audience question and answer. Be sure to type your questions if you have any into the box, and we'll try to get to all of the questions for each of the panelists. And again, thank you very much to all of our speakers for a good job of speaking. And let's move on to some questions and answers at this point, Amy. Okay. Hi, everyone. Welcome back to our panel discussion. We've had a number of questions come in, and we certainly want to get to those questions today. So for Alex, we had a question come in. It says the attendee really wanted to clarify a little bit. It goes back to your hexane extractor, the size. Specifically, they wanted to know about your pilot extractor, about the size of the hexane extractor in tons per hour for soybeans.
Yep. No, thank you for the question. Yep. It's a great question. So we have several extractors in the facility, from small to larger. The one that we use for custom processing for more to simulate continuous production. On a soybean basis, we are able to roughly 300 to 400 pounds an hour, so 150 to 200 kilograms per hour of full fat flakes feeding into the extractor.
All right. Thank you very much. I'm going to move on to our next panelist and try to run through so everyone gets a chance to participate here. Kerri-Ann, we had a question come in, and it says, do foods need to have a certain fat content to measure the oxidative stability?
For foods that don't have a lot of fat content, we have to be able to extract it. And that's done with what's called a cold extraction, where the material is ground up and an extraction process is done with petroleum ether. For the analysis itself, the average sample size is about 5 grams of fats and oils. I would say we could probably push it to 3 to 5 grams, but we have to be able to extract at least that much for the measurement.
Okay, great. Thank you. There was one follow-up question about that, and I think you may have answered it about, is there any sample preparation needed for food products other than pure oils?
Right, yeah, it's just the cold extraction process that I just mentioned.
Okay.
That can be a little bit involved, but it's possible to do that. And we have
All right.
information on those types of analyses.
Yep, great. All right, I'm going to move on and spread the love here about questions. Matthew, we had a question come in for you. It says, can you talk about the accuracy of the chlorophyll and carotene methods when you're measuring color?
Yes, we can measure those parameters. I couldn't tell you off the top of my head, I'm afraid. It caught me by surprise. Because that wasn't the main topic of my conversation.
Yeah.
But if you were to contact me, I'd be delighted to give you to provide the person with a detailed explanation. So just contact.
Yeah. Okay, Amy. Yeah. I think, Amy, if we can refer that question on to Matthew and he can reply directly to the attendee, that will be a great thing.
Yeah, we can definitely measure those parameters.
Great. All right. Moving on down our list of panelists, Ernesto, we had a question come in. It says, what is the utility cost per kilogram of oil processed when using the new short path stripping technology?
That is a great question. Of course, there is a lot of ifs and depends on this. For example, let's take palm oil that is being physically refined by the conventional method of having to strip off literally the free fatty acids through the deodorizer. So the savings in just the amount of steam and energy in having to generate all that energy, we estimate about 50% savings in cost. So it's very rough. Don't hold me to that. Again, it depends on the quality, depends on many things. But in general, we estimate that the savings and energy costs, for example, are about 50%. Now, moving on, comparing to molecular distillation, where this technology, this artisan technology, is able to compete very efficiently, just keep in mind that the short path stripper from artisan has no moving parts. And still is able to produce a molecular distillation, a short path distillation effect. Think of the molecular distillation units, the conventional ones, where you have an internal wiping system that is moved mechanically under very high vacuum with very, fairly expensive sealing system and motors and electrical, consumption there. So there alone, you can see where the savings come from. This short path stripper from artisan having no moving parts inside and being able to do this multi-stage internal distillation system and having the short path effect, sometimes more than 50% savings in energy. And, I can go on the advantages with molecular distillation. You have the disadvantage of having limited size capabilities. With this artisan system, you can make them as big as you need to, as big as a conventional deodorizer, whereas you cannot do that with a molecular distillation system. So, but if you have any more questions, we have only a short amount of time available to us, obviously, but please feel free to write and ask questions.
Okay, great. I'm going to save a few questions for you. We have a number of, let me just see. We have a number of questions for you, but I'm going to move on so we can kind of spread this among our panelists and keep the discussion going.
I'll be very happy to email or to answer questions to the.
Yep.
To the
we have time. We have time. I'm just trying to rotate through each of the panelists with different questions to keep everyone engaged. For Christopher, we had some questions. It says, what is the typical measurement error? I think we may have talked about that a little bit, but maybe you want to comment just so we make sure I get this question answered from one of the attendees.
Sure. So typical measurement error is a very difficult thing to get at right. It sort of depends on the constituent, and then again, in many cases, the wet chem, the primary method being used. Yep. In most cases, so you could expect, depending on, let's say if we're talking for an IV value, if your IV values were from, between 1 and 150, you could expect to be within, plus or minus 1, but actually better than that. Things like free fatty acids, again, depending on the range, you could certainly, depending on whether it's crude, whether it's more refined, you could be within 0.02. 3%, depending on your full range. So again, it kind of depends on the wet method, though.
Yep. Yeah, I agree. Let's see. There was a question here. Follow-up says your protein analysis was that you showed in your presentation. Was this by Kjeldahl or the Dumas method? Chris?
I'm sorry. I didn't.
That's okay. So that in your presentation, you showed a protein analysis. Was that by Kjeldahl or was that by the Dumas technique?
So I don't know what the wet chemistry was for that particular technique. It's not as important what technique is used. We're calibrating to the results that are obtained. So whatever technique you're using is what we're going to use to calibrate to, and that's really the take home of this. Is there's not a preferred or a recommended technique that we give. It's use the one that provides you with the best results, and we'll calibrate to that.
Great. All right, I'm going to try to move back to some other panelists. You have a few more questions, so give me just a little bit of time. I'm going to circle back up and see if we have any other questions here. May have one more for Ernesto here. It says on EPA plus DHA above 50%, but what would be the upper limit? I think they had a question about that ratio.
Yeah, that's one of the bigger issues with concentrating these omega-3s by molecular distillation. The process sort of hits the wall, if you will, by molecular distillation. Basically, to concentrate these omega-3s through short path distillation, you have to use high vacuums and very short residence times and very high temperatures, and also do several passes through the unit to be able to concentrate to higher than 50%. And some processes can go up to 55%. And then from that, it goes on to either urea crystallization or preparatory chromatography, absorptive methods to concentrate to the 85% that these pharmaceuticals, that are prescribed. Actually, these omega-3 ethyl esters are prescribed, as medication by doctors to prevent cardiovascular events. So the advantage of this system of having multi-stage internal systems is that you can mimic several passes through a molecular distillation unit, and it allows you to go to 55, 60%, and this is, we just have started doing this, by the way. The applications just started, so we are, as we speak, doing further tests to see how far we can get by not mimicking, actually. They are actual internal stages in the unit that, for example, with a conventional short path distillation, you have a stage of one, basically. It's one pass, one stage, it goes right through. With this system, with this artisan system, you have multi-stages internally with these distribution plates going through, and you can you can make them as long as you want, as long as necessary to achieve your concentration. So just to answer the question real quick, we don't know yet how far we can go in concentration. Right now, it's way above 55%, and this is information that will come out very soon. And for our next meeting, we will hopefully have a more complete report on this. But it was much higher than the conventional molecular distillation unit as far as concentrating EPA and DHA in these short path systems.
I have one other. That's okay. I have one other follow-up question for you here,
Sure.
and that is, it talks about 3 MCPD esters. They are not very volatile. It asks, is your technology stripping them out of the oil, or is something else happening?
They're stripping them out. We are able to have, again, we have the capability of having very high vacuums. Since we are using an internal condenser, we don't have these pressure drops that you usually have with a deodorizer, for example, or a physical refining system. So by having these internal condenser capabilities, our pressure drop is minimal. So we are able to have very high vacuums and being able to distill them off. So just want to be clear about that. And also real quick, we can also adjust temperatures. These systems are jacketed, or you have the option of jacketing them. So you can adjust internal temperature as well. So you have, again, the option of having a feed temperature and not having a internal jacketed system, or you can have an internal jacketed system and being able to adjust the temperature and go as high or as low as you want. So it's very, very, very innovative in that sense, very flexible.
That's good. All right. Thank you.
You're welcome.
All right. I want to move on down. I had another couple of questions come in for you, Christopher. It says, can you determine solvent such as ethanol or hexane extracted oil ratio in line?
Yes, you should be able to. With some of the solvent extractions, they shouldn't be able. You can look at. I would assume this would be for something like a flakes application or something in that. Yes, in fact, we are working on that in a variety of applications currently, projects that we're doing for them.
Okay. I think that there's a few questions here about calibration, and maybe we can run through those real quickly. It says, does an NIR device need setting up on site by an expert, or does it, and I think this is a separate question, does it come fully calibrated from the factory?
So depending on the, for an inline instrument, there would of course be installation and setup. Depending on the application, Bruker does have a catalog of calibrations for a variety of constituents and a variety of product types. What is often required is if not always a full calibration development, but at the very least, we'll usually need to take some samples, excuse me, and sort of integrate them into a model. So, apologies. So basically, if you, seed, what we call seeding a calibration, if it's already developed, that will kind of allow it to learn for any little differences that might be that might be different from the product at a given site versus a master calibration that was developed, and that's just part of sort of a model maintenance that is often done. But one of the things about the transferability of the calibrations is a lot of times, if you can develop a calibration at a site that has the resources to do it, the lab resources, you can send those calibrations out to other sites without having to do the setup and the work. You can just put them in and begin using them because of the ability to transfer calibrations between spectrometers.
All right. There's one other question about calibration. It says, which compound is used to calibrate the fat content measurements?
I'm not sure I understand when they say which compound is used to.
Yeah, I guess the question might be maybe better answered is, fats have there are a range of individual molecules that make up fat content, molecular weight distribution. Sure. And so would you use that, or maybe you might use something like a supercritical fluid extraction method as a primary method versus trying to have a single component method for calibration?
Right. So again, it's not as critical what primary method you use. Typically, when you are looking at an NIR spectrum, you're going to have regions that calibration is going to sort of key on when it develops the model. So the software is going to looking for changes in spectral features, shifts, absorbance changes, and it's correlating those to the wet chemistry changes that are input based on that primary method. And what you'll typically see is where the region of the calibration will choose for fat will be the CH stretches that are present in the spectra themselves. So you'll see that it tends to choose the regions where that variation is most pronounced relative to the wet chemistry. And again, that's just a natural result. That's the physics of spectroscopy and where the fat content presents spectroscopically.
Yep, I think there's one last question here for you, and it says, can you sense in line the concentration of extracted oil in the solvent, or in other words, determine the oil solvent ratio?
Sure. So, I mean, that, when you can determine either a constituent or multiple constituents, you can always mathematically arrive and at a ratio, or you can perform a calculation and actually have your results presented or sent back as a ratioed or a calculated value.
Yep. Okay, good. Thank you very much. So I just want to remind our audience, if you have questions for our panelists, please type them in. We want to make sure that if you have questions, that they get addressed and answered by our panelists. We have a few more minutes in the question and answer session here, and I think we've run through most of our questions at this point, but I would really appreciate it if you have some additional questions. Please type them in at this time so that we can have our panelists answer those questions, or at least try to address the questions that you might have on any of the presentations. I'm going to look here, see if any more questions are coming in. And at this particular point, I don't see any new questions. So I guess on the behalf of the AOCS, Amy, at this point, I don't see any additional questions, but on behalf of AOCS, I want to thank each of our speakers today for preparing a good presentation for our audience. Certainly, we've had a lot of questions. I think there's a lot of interest in the content that you've delivered today. So on behalf of AOCS, thank you for participating and sharing with us the results of your work and your findings. And again, audience, thank you for listening in to us. If there are no more questions at this time, I think, Amy, we might actually end the session a little bit early, unless there's some more questions coming in that I don't see here.
No new questions. So thank you, everybody. I think you can close us out, Larry.
All right. Well, listen, thank you very much for your participation. Hope everyone has a great day. And again, please take a look at the AOCS schedule. There are additional sessions of interest many of our speakers here have additional presentations, and I'm sure they'd love to have you participating in those panel discussions as well. So again, thank you very much for joining us today, and I hope everyone has a great day. And thanks for joining and supporting our industry through AOCS.